The energetics of evaporation. So evaporation is endothermic, meaning we have to put energy into this process to cause the water to evaporate. Our bodies make use of this to cool us when it's hot outside. It's supposed to be 93 today, and so we will probably be sweating this afternoon. Why does sweating cool you off? Sweating causes moisture to appear on your skin. As that evaporates, it takes energy away from your skin. So for the water, the moisture that's evaporating, it's an endothermic process. Heat energy is coming in. Where is the heat energy coming from? It's coming from your skin. And so that's why when you sweat and there's a bit of a breeze, it feels cool because of the evaporation. Because what's really happening is it's the more energetic particles that are evaporating first, leaving behind the lower energy particles. And it's the principle behind a swamp cooler as well. Any questions about sweating? I don't give advice on deodorant. Energetics of condensation. So condensation is the opposite of evaporation. Condensation is exothermic. It actually gives off heat. And this does not make sense intuitively. Something condensing gives off heat? That doesn't make any sense at all. The way to remember it is evaporation requires energy to be put in. If you think about how can you make something evaporate faster? Well, heat it up and it'll evaporate faster, right? So we can intuitively figure out that evaporation is endothermic. Condensation is the opposite process. It has to be opposite. If one's endothermic, the other has to be exothermic. Have you ever burned your hand over a hot pot of water? Or almost? You want to be real careful when you're boiling water on the stove. Obviously, you don't want to spill the water on yourself, but if you put your hand in the steam over the hot pot of water, that is really hot. And that can actually burn you worse than the boiling water itself, because that steam carries a tremendous amount of energy. And when it condenses on your hand, it releases all of that energy into your skin and can cause a pretty bad burn. The exothermic nature of condensation moderates climate. Now, we live in a very arid region, and so we get wide temperature swings during the day. It might be 60 degrees at night and close to 100 during the day, right? In the summer, that can happen. In other places where there's higher humidity, that doesn't happen. I grew up in the Midwest, and it might be 90 during the day, and it would get down to 80 during the night, because it's like 90% humidity. And what happens as the air temperature cools, the moisture in the air condenses on everything around and gives off heat. And that causes the temperature to stay high. Those times in the summer when it becomes really uncomfortable, it's humid, it's more humid. It's not anything like Minnesota, but it's humid for us. And I've been here long enough that it feels muggy to me, even when it's only 50% humidity. But it just feels icky outside, right? And you sweat, and it just doesn't help that much, right? So the humidity in the air moderates temperature. If you've spent any time at the coast, you probably notice that their temperatures do not fluctuate nearly as much as they do here in the valley. Because there's the ocean and the San Francisco Bay, those huge bodies of water moderate the temperature. There's evaporation during the day, which helps to cool things off. There's condensation at night that helps to warm things up. So it moderates the temperature. It happens around the Great Lakes and anywhere at the coast. The temperature is moderated by large bodies of water. Heat of vaporization. Okay, so now we're going to get to some numbers. I feel like I skipped something, but no, there's nothing in there. Okay, so vaporization is an endothermic process. It requires energy. How much energy? Well, we use heat of vaporization to quantify that. Heat of vaporization, which is abbreviated delta H vap for vaporization, is the amount of heat required to vaporize 1 mole of a liquid. The heat of vaporization of water at its normal boiling point is 40.7 kilojoules per mole. So to vaporize a mole of water at the boiling point requires 40.7 kilojoules for every mole of water. So that's for every 18 grams of water. And we can express this in a chemical equation this way. Liquid water is being transformed into water in the gas state. Delta H equals plus 40.7 kilojoules. This is positive because it's endothermic. The energy is going into the system. You put yourself in the position of the system, and energy coming in is like money coming into your wallet. You feel positive about that. Negative energy is going out, like money leaving your wallet. That's a negative experience. This amount of energy is for the molar quantities listed in the equation. So 1 mole of water to 1 mole of gas requires 40.7 kilojoules of energy. When we condense gas into liquid, it is the opposite process. It is a physical change. It is reversible. It releases the same amount of energy. So when we have the gas going to the liquid, delta H has the same value, but the sign is different because now the energy is being released. Any questions? So we can use heat of vaporization to calculate how much heat will be required to vaporize a certain amount of liquid, or how much energy will be released when a certain amount of liquid condenses. These are not numbers you need to memorize. They'll be provided to you on an exam, but you might have to look them up in this table when you're doing the homework. So here's water. The heat of vaporization is going to be slightly different depending on the temperature. This is at room temperature. This is at the boiling point. And the boiling points for these liquids are listed right here. So isopropyl alcohol, that's rubbing alcohol. You go to the doctor and they're going to give you a vaccination, and they rub something on your skin. You're like, wow, that's cold. Alcohol evaporates more easily. So the heat of vaporization, it actually takes in more heat than water does, and that's why it feels cold. More cold than water does. So these act as conversion factors, kilojoules per mole. So let's do an example. Calculate the amount of heat required to vaporize 25 grams of water at its boiling point. The heat of vaporization is 40.7 kilojoules per mole. So there's 2 numbers in this problem. We've got 25 grams, and we've got 40.7 kilojoules per mole. Which one of those looks like a conversion factor? The kilojoules per mole, right? This could be used to convert between kilojoules and moles. So what are we trying to find? The amount of heat, right? What's a unit of heat that's showing up here? Grams, kilojoules, moles, kilojoules. So we want to find, I'm going to write my path up here at the top. We want to find kilojoules. Sometimes it's hard to know which of these numbers to start with, but this one looks like a conversion factor. That one's not going to convert anything. So that's probably the one we're going to start with. We're going to start with grams. Do we have a relationship between grams and kilojoules?
Yes.
Directly? No. But we have kilojoules to moles. So if we had moles in here, can we get from grams to moles? Yeah, molar mass. So there's our path. So actually I'm just going to take this guy right here, 25 grams of water, and we need to convert to moles of water, and then to kilojoules. And then just following our pattern for dimensional analysis, I'm going to divide by grams here, grams of H2O. So those units cancel out. And I'm going to divide by moles of H2O here. Those cancel out. Units. Kilojoules and moles. Well, that's this guy they gave us in the problem. 40.7 kilojoules. And that's per 1 mole. And then how do we find this guy in the middle? It's 18.02, yes, some of you have it memorized. 2 times the mass of hydrogen plus 1 times the mass of oxygen. Add them up, calculating a molar mass. So 1 mole of water weighs 18.02 grams. So 25 divided by 18.02 times 40.7. That gives us 56.5 kilojoules. Any questions? Here's another example. This one's a little more complicated. You can tell by all the words. A drop of water weighing 0.48 grams condenses on the surface of a 55-gram block of aluminum that is initially at 25 degrees Celsius. If the heat released during condensation goes only toward heating the metal, what is the final temperature in Celsius of the metal block? The specific heat capacity of aluminum is 0.903 joules per gram degree Celsius. So I'm looking at this and I'm thinking, did we cover this? Did we do Q equals MCAT? No? Some people are saying yes. Q equals MC delta T. Pretty sure we did that. Q is energy.
Yeah.
Okay. So this is what I would consider a challenging problem for Chem 20. So let's think about what's going on here, and sometimes it's helpful to draw a picture. So we've got a block of aluminum, right? So here's a block of aluminum. And the block of aluminum weighs 55 grams. And it's at 25 degrees Celsius. So 25 degrees. And what's happening to that block of aluminum? Something about a drop of water, right? So here's a drop of water. And the drop of water weighs 0.48 grams. You read that okay? It's a little high, a little dark. Let's go with, change the color a little bit. Is that better? 0.48 grams, that's the mass of the water. Drop of water condenses. The heat released during condensation goes only toward the heating of the metal. So let's think about, so we have water condensing onto that block of aluminum. Is that going to absorb heat or release heat? It's going to release heat. Could we calculate the amount of heat that is released by the water? Yeah, we just learned how to do that. We're going to need the heat of vaporization, though, right? Is this occurring at the boiling point of water or at 25 degrees Celsius? At 25. So we need to go back to our table here. The heat of vaporization for water is 40.7 at 100, but at 25 it's 44. kilojoules per mole. So delta H for the water is 44 kilojoules per mole. So we can help calculate Q, the heat released by the water. That's the 0.48 grams of water times 1 mole of water divided by 18.02 grams of water. The grams cancel out. Times 44.0 kilojoules per mole of water. So 0.48 divided by 18.02 times 44. 2 sig figs, but I'm going to carry 2 extras. 1.172 kilojoules. And where does the problem say that that heat went? Into the block of aluminum. So this equation up here, Q equals mc delta T, that's the heat is equal to the mass times the specific heat capacity of the aluminum, which they gave us right here, times the change in temperature. And they're wanting to know what's the final temperature of that block of aluminum. That is not what I wanted to do. Thankfully, I've learned how to undo that. This is a problem. So all of this energy went into the block of aluminum. So that's this Q. Actually, let me go up here. What we want to do is we want to rearrange this and solve for delta T. So the change in temperature of the block of aluminum equals the amount of energy divided by the mass times the specific heat capacity. So delta T is the mass of the block, which is given as 55 grams. No, it's the Q, sorry, 1.172 kilojoules divided by 55 grams divided by 0.903 joules per gram degrees Celsius. The grams will cancel each other. Do kilojoules cancel joules? No. Bummer. What does kilo stand for? 1,000, or 10 to the 3. So what I can do is I can, instead of writing kilo, I can write what it means. 10 to the 3 joules. You could also do it separately in a unit conversion. The joules cancel out. So now I've got 1.172 times 10 to the 3rd divided by 55 divided by 0.903. And this is telling me 23.6 degrees Celsius. Is that the final temperature? That's the change in temperature. How do we figure out what the final temperature is? We use the initial temperature. So it started at 25. There's different ways to think about it. You can use the equation, delta T equals T final minus T initial. Or you can think about it, the water was releasing heat. Is the temperature going to go up or down? It's going to go up. So this is the change. We need to add that to the initial temperature. So we've got 25 degrees Celsius plus 23.6 degrees Celsius. This is a 48.2 0.6 degrees Celsius, which would, with sig figs, come out to be 49. Any questions? That one's a little much to take in at 8:30 in the morning, isn't it? That's putting two skills together, is what that is.